Hello, my name is Henrique, and I'm going to present the paper with the title Safety Through Intrinsically Motivated Imitation Learning. So, during this presentation, I'm going to talk about the pump scheduling problem, show the representation that we propose of this problem as a partially observable Markov decision process, talk about the motivation of our approach, Safe Truth, Intrinsically Motivated Imitation Learning, and finally, I'm going to show some results that we're obtaining. So let's start talking about the pump scheduling problem. So here we have a real-world water distribution system. It's a water utility located in Worms in Germany, which supplies water for about 120,000 people. Basically, we have a raw water source, and then we treat this water and put this water in a reservoir. And then we have a decision process that we found suitable to model as a Markov decision process. Basically, we have 4 pumps with different settings and fixed speed. At each time step, just one of them can be running or none of them. And they have, as I said, they have different settings, which means that the pump NP1, for example, is more powerful than NP2. And also, when I say fixed speed, because we can just turn on or off the pumps, we cannot choose the speed. So the idea is, regarding the forecast of water demand, choose the most suitable pump and pump this water through the system until tanks which are placed near to the end consumers. So the question is, which pressure is necessary to deliver a certain amount of water into the system? For that to have some constraints, such as water demand has to be delivered, storage tanks must not overflow or run out of water, a minimal water reserve has to meet the tanks, and a minimal pressure must be guaranteed in the pipe network. These two last items are related to the safety constraints. Pumps must be operated efficiently, which means that we should operate the system, for example, trying to minimize the electricity consumption. And finally, we must guarantee the water exchange in the tanks in order to preserve the water quality. So here we have characteristics of the water utility in Worms. We have 3 years of data collected in time steps of 1 minute. For this system, in the first chart, we have the water consumption pattern. And as you can see, there is a peak in the water consumption between 8 and 9 a.m., probably because people is going to the work, and then later we have another peak between 7 and 8 p.m., probably because people is coming back from the work. In the second chart, we have average electricity consumption per month. The idea here is that we should find a strategy which minimizes the electricity consumption. In the third chart, we have tank level per month, and as you can see, there is a kind of strategy or policy being applied currently in the system. Basically, they fill the tanks in a high level before of the peak in the water consumption, and then they let the tank decrease along the day to provide exchange and preserve the water quality. This is one of our motivations. We think that we might have a different strategy that can meet the safety constraints and also save more electricity. In the last chart, we have average switch on-off per month. The idea here is that we should avoid switch the pump operation, because doing that we decrease the lifetime of the pumps. So let's introduce our approach, Safe Through Intrinsically Motivated Imitation Learning. Our motivation is that, as many real-world problems, we have a high-dimensional state space with safety constraints. So exploration strategies may struggle, for example, to figure out that we must hold an action selection for a long period or many time steps, because we have a constraint regarding the switch the pump operation, right? And then also counter-based methods that try to uncover areas of the state space may lead us to meaningless states. So the idea is that we can use demonstrations, and learning from demonstration has been shown that can be quite sample efficient. For example, in offline reinforcement learning, we use logged data and we don't interact with the environment, and only using this data we can learn a policy or we can use the demonstrations to guide the interactions with the environment as imitation learning does. So basically, in the water distribution system of worms, we have a simulator given by experts, and then we adapt the simulator to the Markov decision process settings. So given initial condition, for example, tank level in certain time step, we use real-world data regarding the water consumption as input, and then we can build a state. So given state, we can apply an action which corresponds to choose one of the pump or turn all of them off. So applying this action, we can calculate the next tank level for the next time step, as well calculate the flow, the electric consumption, and the pressure for this time step. So basically we have a state, we apply an action, and we get a new state. So the first step of our approach is to perform a density-based action selection using the k nearest neighbors and also using as a distance metric the Manhattan distance for this particular case. The idea here is that given a state using the simulator, I take the demonstrations and then I query which are the most similar states regarding my current state. And then I check the action that were applied in these states, which are my neighbors, and I choose the one that was mostly applied the most similar state to my current state, and then I apply this action again. When I have the state and apply an action, I move to another state and get a reward for that. This reward is the extrinsic reward. So then we augment this immediate reward received using an intrinsic reward, and we balance the importance of this intrinsic reward through an importance factor rho. The idea here is we add a bonus according to the state likelihood under the demonstration distribution, where the state is my current state. Or hypothesis that undesirable states tend to occur less often in the demonstration distribution, and consequently they get a lower bonus for the density, where familiar states are familiar, they lie in region of high density, then consequently you get a higher bonus for the relative density. Also, we have the problem of overestimation in the face of uncertainty when you exploit the dataset. States that are out of a distribution tends to be overestimated. So this intrinsic reward works as a penalty once that state out of distribution are also those that get a lower bonus for the relative density. So the next step is propose a representation for the pump scheduling problem as a partially observable Markov decision process. So here we have the state representation, and the states and the observations are interchangeable in the context of this work. We have the actions. We have one action for each pump and also the option to not operate. And we design two reward functions because we want to evaluate the adequacy of the behavior that emerge applying these two distinct returns. In the first reward function, we have the first term here where we give a positive value for the efficiency, and we do that taking the flow divided by electricity consumption. In the term in the middle, we penalize when you don't meet the safety constraints regarding the tank levels. And the last term, through the variable p, we penalize the cumulative time that some pump is operating, and in the variable omega, we penalize when you switch the pump operation. And the second reward function is quite similar, but instead of giving a positive value for the efficiency, we penalize the electricity consumption directly. So then we have the results. For that, we compare our approach with two offline reinforcement learning methods as a baseline, the discrete version of batch-constrained deep Q learning, and the random ensemble mixture. So for each reward function, we obtain 5 policies using each of these methods. So here we have the average cumulative reward for the reward function 1. So in the chart at left, we have the cumulative reward along with the episodes. We use one year of data to evaluate these methods, and the lower peaks in the chart are mainly due to not meet the safety constraints regarding tank level. And as you can see, our method combined with a random ensemble mixture achieve a better average cumulative reward compared to random ensemble mixtures only and batch constrained deep Q learning. In the chart at the right, we can see that also we achieve a lower variance compared to the other methods. And finally, comparing our electricity consumption regarding the human operation, we could achieve in the average, using the 5 policies, an average of less 4% of electricity consumption. Here we have the average cumulative Hilbert for the Hilbert function 2. And we also, in this using this Hilbert function, perform better than random access mixture, but worse than the batch-constrained deep Q-learning. But at the chart at right, we can see that also we achieve lower variance compared to the other methods. And finally, comparing our approach with the electricity consumption regarding the human operation, the average of the electricity consumption was lower also than human operation, around 3%. And then we conduct a sensitive analysis regarding the importance factor ρ. We consider the ρ equal to 0, which means that we don't give a bonus, we don't give an intrinsic Hilbert, we don't augment the Hilbert function. We use ρ equal to 1, that the value was used in the previous experiments, and we increase this value by 5 times. In both cases, ρ equal to 1 performed better than ρ equal to 0. But in the case of ρ equal to 5, for the second Hilbert function, we perform worse than ρ equal to 0. We believe that the reason behind of this is that when we augment the Hilbert function, we change the policy being learned, and that might be contradictory to the other policy sub-goals. We would like to thank our partners in the project IoT Water, from the Technical University of Kaiserslautern, Federal University of Minas Gerais, University of Liège, and also the company Dr. Kretzig. And also, we would like to thank the funding of this project, in particular, the National Agency of Research, ANR, in France. If you have some questions, we have a Q&A session, and also you can send me an email. Thank you for your attention.